Okay, so we want to find an easier way to do our coefficients, to find our coefficients for our Newton interpolating polynomials. So we're going to study a method called divided differences. And so we'll start off as usual. We'll have n plus 1 distinct points, x0 through xn. And we'll define some polynomials with respect to these points. Well, first, q0 is the constant polynomial 1. q1 will be x minus x0. q2, x minus x0 times x minus x1. And then we'll continue in this way till we get qn is x minus x0 times x minus x1, and so on to x minus xn minus 1, okay? And we'll say that our polynomial then is px is the sum from j equals 0 to n of c sub j times q sub j of x. Okay, so again, this is the basic setup for the Newton polynomial. It's just dressed up a little differently. Okay, now, instead of using y's for our values, we're going to shift to a functional notation. Say we have our data in ordered pairs, x and f of 0, etc., to up to x sub n time, and f of x sub n. And so where we want to have our polynomial interpolating f at these values. Okay, so we'll consider now the sum j equal 0 to n of cj times qj of x sub I, okay, equals f of x sub I. Okay, and we'll put so this is a system of linear equations. We can put it into matrices as below, where we have an A matrix, which is actually has the Aij coming from these terms right here. Our Cj again from here, and the constant column here. So again, it's a system of a matrix equation, a system of linear equations. So the Cj we're looking for is the solution to this matrix equation. So, for example, let's consider the data where x is equal to 0, 1, and 2, and where our y's are 1, 3, and 5. If we do it this way, then our q0 of x is equal to 1, our q1 of x is equal to x, and our q2 of x is x times x minus 1. This will give us a system that 1, 3, and 5 is equal to C0 times Q0 of 0. C3 is equal to C0 times Q0 of 1 plus C1 times Q1 of 1. And finally, 5 is equal to C0 Q0 of 2 plus C1 times Q1 of 2 plus C2 times Q2 of 2. And this gives us a matrix equation that we can solve by the sweep out process. But notice this is going to be simpler, right? Because the upper triangular part is 0. Okay, so there will be a special way to solve this that we won't have to break down and go to special software to do it. This matrix was come about from very specific values. Let's go and let's look at it in a more general way. So, for instance, each of the CK depends upon F0 through f of xk. So it only depends, it doesn't depend on all of my f values, but only of the values that appeared before this step. Okay, so this means that we can make a notation for our CK that only depends upon those values, and this notation will be f of square brackets x0 through xk. And so we're going to just plop that in, and it's a bit longer, a bit more cumbersome, but this will have a payoff later when we start doing these by hand, as it were. So let's now look at our q sub n of x, which is this product of x minus x0 dot 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 through x minus x sub n minus 1. If we multiply those all out, the leading coefficient is going to be monic, because there isn't any coefficient tied to any of these isolated x's out front. So this will be, my qn of x will be x to the n plus lower degree terms. So when we get to the end, the largest one of these is this f of x0 through xn is the coefficient of the highest degree term in p of x. Okay. The name that we give to these f of x0 through f of xj are, well, these are called divided differences, and we'll justify that name momentarily. Okay, so let's suppose we have the simplest possible system where we just have two values, okay, and we roll this into one of our matrices, okay, as we would if we were evaluating. And the form we would have on this is 1, 0, f of x0 along the top, and the second row would be 1, x1 minus x0, f of x1. If we go through a sweep out process, adding the negative of the top row to the second row, this will have this effect on the matrix, where we'll have the second row will become x1 minus x0, and then f of x1 minus f of x0. Now, to create a consistent notation, what we're going to do is let this f of x0 be equal, this f of square bracket of x0, we'll define it to be f of x0. Okay, and so we and define our coefficient here, the C1, the f of x0, x1 will be the solution to this system, which is f of x0 minus f of x1 minus f of x0 over x1 minus x0. And again, here we have the same thing. We're putting in the square bracket notation. Okay, so that's the first thing. So this guy will equal to this guy. All right, now let's take it up to the next level of complication. Have one more point. And you can, pause here, copy this down, and run through and check my math. But if you run through it, okay, and again here finishing it up on this page, if you run through it and simplify, what we see is that these my solutions are going to be these divided differences. Okay, again, where the most pertinently this last divided difference here. Let me get that. Arg. This guy is equal to this guy divided by this. So again, you get it, divided differences. So this is a difference of things that come above it and divided by so. The language makes sense. Okay, well chosen notation. Okay, and so this brings us to the divided difference formula. Okay, so we've got the divided difference formula, and it's strange looking, okay? All these square brackets, and we have things that's going to require some work to remember, at least if you're like me. What do you want to focus on? Here we have x0 through xn, but here we only have x1 through xn, and here we have x0 through xn minus 1. So what's sort of happening here, and we're dividing by xn minus x0. So you can try to remember this a couple of different ways, that this number is the same number as this one, and this number is the same number as this one. Or you can think, okay, this guy flies off, we lose the x0 off the front, he flies off and winds up here. We lose the xn off the end here, he flies off, and other side. That's one way to remember it. I'm going to work out some examples by hand for you, so you shouldn't have to remember it like that. You need to work through some examples to get this in your muscle memory. Okay, but let's look at one first. Okay, so I have my data: 3 paired with 1, 1 paired with -3, 5 paired with 2, and 6 paired with 4. I start out just going through by definition. Okay, if you do this, you get for F3, 1. I'm trying to eventually want to work out F3, 1, F3, 1, 5, F3, 1, 5, 6. That's what I'll want to do. Let's start out first, F3, 1. I do f of 1 minus f of 3, f of 3 minus f of 1, over 1 minus 3. I do arithmetic there, get a 2. And I'll want to put that number here. Okay. Then I'll do f1, 5. I run through it formally, get 5/4. That number will go here. F5, 2, and go through its formula and get a 2. That number will go here. And then continue. So I got 2, 5/4, 2. I'll then go F315 and go through its formula and get the 3/8 here. Go F156. Go through its formula, get the 3/20 here, and then finally go the F156, run through that formula and get the 7/40. Okay. And let me go back on this. Pardon me. right. That my polynomial then will be 1 plus 2 times x minus 3 times minus 3/8 times x minus 3 x minus 1 plus 7/40 x minus 3 times x minus 1 times x minus 5. Okay. Okay, we can do this by, can set up a couple of different algorithms for this that are easily computable. You can put these into code without much trouble. Just your C array, output array. It'll be a two-dimensional array. You set it up like that. The second one, we can set it up as get your answers out in a one-dimensional array with just a little bit more complication in coding. And so the theorem, let P be a polynomial that interpolates a function f at x0 through xn. If t is not one of the nodes, then f of t minus p of t is this divided difference thing times the product, which this will give us a way to estimate error, okay, using our divided difference. Okay, so here on our example we have our data where 3 is paired with 1, 1 is paired with -3, 5 is paired with 2, and 4 is paired with 6. And we want to start a procedure where basically we don't have to think about what we're doing, and we can forget about the notation and just let our muscles do it. So our first column is going to be 1, 3, 5, 6. And our second column is 1, -3, 2, 4. And we're going to calculate this and fill out our data like that. So we'll first go with our first two rows here. I'll go -3 minus 1 over 1 minus 3. This will be -4 over -2, which is 2. And so this number here becomes 2. I now go down to the next two. Here on this first step, I'm keeping my indices 1 apart. And so this next one, I'll go, okay, 2 minus -3 over 5 minus 1. This will be 5 over 4. And so in this spot, I'll put a 5/4. And now we'll go down to the bottom two. Okay. On the bottom two, I'll have 4 minus 2. And then I'll have 6 minus 5. This will give me a 2 on the top and a 1 on the bottom, which will give me a 2, and so I put a 2 here. Okay. Now this next step, I'm going to be farther apart on my indices. Now, my top, I still take I'll be taking my difference from this column. On my bottom, I'll take my difference from this column. So the top, I will take 5/4 minus 2. On the bottom, I'll go 5 minus 3. And so my denominator, 5 minus 3 is 2. My numerator, I have 5/4 minus 2, which is 8/4. So this is 1/2. Okay, 5 minus, that's -3 over 4. So this is -3/8. And so -3/8. All right, now I'm staying the same distance apart, but I slide down. Okay, and so let's see, the top I'll have 2 minus 5/4. On the bottom, though, I'll have 6 minus 1. Okay, so be 1/5 times, okay, 2 minus 5/4, that's 8/4 minus 5/4. Okay, 1/5 times 3/4, that's 3/20, and so this is 3/20. And so I'm done on that one. Now the last one, the numerator, I will have 3/20 minus negative 3/8, and on the bottom, okay, I'll be going 6 minus 3. So I'll have 1/3, okay. Okay, 3/20 plus 3/8, so this will be 6/40 plus, okay, 15/40. This will be 21/120. And so the polynomial will be, okay, P of x is equal to 1 plus 2 times x minus 3 plus, minus 3/8 x minus 3 x minus 1 plus 21/120 x minus 3 x minus 1 x minus 5.